So thank you everyone for joining today's LF Decentralized Trust meetup. We are talking today about making zero knowledge smart contract development accessible, secure, and practical. This is about the brand new Minakawa project that was recently approved and is going to be hosted by LF Decentralized Trust. And today we have one of the maintainers of that project, Kevin Millikin, who will be talking about it. So Kevin, please take it away.
Thank you, David. So, as David said, the title of the talk is Making Zero Knowledge Smart Contract Development Accessible, Secure, and Practical. And every single word in that title, except for maybe making and is super important. So I'll try to talk about all of those. Just a caveat: I won't actually make any strong security claims. Security will be sort of salted throughout the whole presentation, but I'll talk about everything else in this. The plan, I'm going to start with some real generalization, some real abstraction. Hopefully you will find that to be a real gentle introduction into the idea of security and privacy in the blockchain context. That One really important thing that I'll talk about up front is what we call the Kachina model. So this was based on a sort of an academic or theoretical model of what a privacy-preserving smart contract language would be, and this is the programming model that we've embraced with Minakawa. And then we'll get into talking about some of the concrete details of how it's implemented on the Midnight blockchain, and then we'll generalize a little bit more to talk about how it's not really a Midnight-specific technology that we've developed. So the first thing I want to talk about is just smart contract development and make sure that everybody has a good understanding of what we mean by smart contracts. Um, so abstractly, a smart contract is just a state transition system. There's some state. I wrote this, I labeled the states S sub I, SI plus one, SI plus two, and there's some transitions. The transition takes an input state and maps it to an output state. So this is kind of abstractly what we're talking about. This model is not, this is too general. So this actually just describes programs in general. So on my phone, I've got an ARM processor and I've got a memory, and the state of my phone is the memory, and the transitions are ARM instructions that the processor is running, and they're causing the phone to go through state transitions. So I wouldn't normally think of the software on my phone as a smart contract. So we mean a little bit more than that, and let's build that up in layers. So we've got these states. Um, and generally, we mean the states are in a blockchain. They're recorded on a blockchain. Um, so that's pretty important to what we're talking about when we talk about smart contracts. A decentralized blockchain. So blockchains don't have to be decentralized, but we generally mean that a smart contract system is running in a decentralized blockchain. And this is important. There's no centralized authority that can go in and change the state of the contract other than what the rules of the contract allow. So the contract may allow the contract may be coded to allow a centralized authority or an authorized person to make certain changes that the general people can't do. But the blockchain itself does not allow that in a general way. And then an important consequence of this is that these are public states. So the fact that they're in a decentralized blockchain means that all of the participants in the blockchain can see these states. There's no information hiding at all. That if we wanted to hide information in the public state, we would have to do something that was outside of the chain, like encrypting the state and decrypting it outside of the chain, so that it couldn't that somebody who was just looking at the state of the blockchain could not understand what that was. And then the next thing we'd like to think about a little bit is these transactions. So I use T. It's a state transition, but it's also kind of ambiguously a transaction. We think of a blockchain, a smart contract blockchain, as supporting transactions, where a transaction is a request that the blockchain performs a transition on a state transition for the smart contract. And these are defined by rules. The rules are represented in code. A very, very successful example of a smart contract system is the Ethereum system. And so there, the chain is actually running a bytecode language called Ethereum, Ethereum Virtual Machine. But the contracts were probably written in a language like Solidity that was translated into that language. And an important part of the puzzle is that the transactions are defined by fixed rules. So by this, I mean that the rules don't change once we've deployed the contract. The contract is deployed, and it has rules that are encoded in the code of the contract. And it gets a little bit back to the idea that we have a decentralized blockchain. Once we've deployed the contract, the rules of the contract specify how the state is transitions, and there's nothing else other than the contract source code that can govern how the state transitions. So the piece that was missing from there, if you picked up on it, is that there's nothing private about the state of a smart contract system, an Ethereum style state smart contract system. There's nothing private. There's nothing inherently private. You could do something that was outside of the chain to try to implement privacy. We're going to try to build privacy into a blockchain context, and we're going to use something called zero knowledge. So zero knowledge sounds like maybe it's bad, like we don't know anything, but it can also be very good, and you'll see why. And the important thing to understand about the way that we're talking about privacy preserving blockchains is we've adopted a particular programming model. There are other programming models, and we've adopted one that's based on a work called Kachina. We're going to add privacy to the blockchain. The very first thing we'll do is we'll recognize that the state that we're talking about in a smart contract system could actually be split into a pair of states. If you're used to a system like Ethereum, when you think of a decentralized application or a DApp, there are pieces of code that run on chain and there's pieces of code that run off chain, and you can kind of split the code into on chain and off chain code. We're going to make a similar split in a different direction, which is we're going to categorize the state as private and public state. So I represent public as U, that's the second letter of the word public, and I represent private as R, that's the second letter of the word private, because I can't use P for both of them. So the very first thing I want to do is I want to split the state of the contract into pairs of states, so that I can talk about a pair of a public and a private state, and then a transaction would modify both the public and the private part of the state. So this is the first step. Now I can't just put this on a public blockchain because the private state is right there, and that's the part that I don't want to put on the public blockchain. So I need to keep that off the public blockchain. So this I can't just put on the public blockchain. And now you might think, well, let's just put the public state on the public blockchain. We'll keep the private state off chain. So this is a picture of just the public state, the U state, on the public blockchain. And we also can't put this on the public blockchain. And this is for a different reason, which is really subtle, but very important. The evolution of the state from U sub I to U sub I plus 1 caused by that first state transition, that depends on the private state. And so if the blockchain doesn't have any notion of the private state at all, and it's asked to perform such a transition, it doesn't actually know if it's a valid transition for it to perform. In other words, the contract can't enforce its own rules. The rules of the contract might require certain characteristics of the private state, and that the blockchain cannot enforce that. So you could potentially ask this blockchain that has only public state to perform an invalid transaction that was just not valid within the context of the contract. So we want to allow contracts that can actually talk about the private state and that can impose constraints or requirements on the private state, but without recording those in the blockchain. So we need to take a digression into zero knowledge. So this is very interesting. I am not an expert, so I'm going to do a very sort of high level overview of zero knowledge. The very, very important concept is what in the way that we've used zero knowledge is something called ZK SNARKs. So what is a ZK SNARK? There's a lot of words in the definition of ZK SNARK too. And again, they're all important. I'm going to gloss over most of those, and I'm just going to talk about it's a protocol between two participants, the prover and the verifier. So the prover is going to construct a proof, and it's going to send the proof to the verifier, who will verify the proof. There's a few important things about this protocol. So one is that the verifier, the proof is a proof about private data, and that the verifier can't learn anything about the private data from the proof. So that's the zero knowledge property. There's another word in the SNARK, which is the S, which is the succinct. Succinct means short. Um, the idea is that verifying the proof is fast, fast relative to making the proof. So this is very similar to computing a hash of a message versus verifying a hash of a message. Computing the hash or encrypting a message might be slow, but verifying is fast. So we want a similar property here. And then we also want a certain sound and completeness property that I think is I won't talk about too much. So an interesting result, an early result, is that ZK SNARKs exist for a lot of problems that we're interested in, and the way that we get a hook into this result is that there's a demonstrated to be a ZK SNARK protocol for a specific problem, which is called graph 3 colorability. So given a graph where I have vertexes and edges, and the edges represent connections between vertexes, I'd like to ask if it's possible to color the graph with 3 different colors. I would like to convince the verifier. So the prover would like to find a coloring of the graph and convince the verifier that such a coloring exists without revealing the secret of what the coloring is. And there does actually exist a protocol for this. It's interesting. It's technical. I won't go more into it. Why it's important for us is that there is a related problem called 3-sat, which is Boolean satisfiability with where we have clauses that are consist of disjunctions of 3 variables. Conjunctions of clauses that consist of disjunctions of 3 variables. We can encode that 3 coloring of the graph into a big Boolean formula, and we can ask if it's satisfiable. Are there assignments of true and false to the variables that make this formula true? And so this is a problem that is more general than the graph 3 coloring. We can encode the graph 3 coloring in this problem. And another related problem is what's called arithmetic circuit satisfiability. We can encode the 3-sat problem into this one. And this one is super useful for us because we not only know that ZK SNARKs exist, but we actually know how to find them. And so we can actually build, if we represent a problem as an arithmetic circuit satisfiability problem, we can actually build a ZK SNARK. And keep in mind that what we're trying to do, keep in mind that what we're trying to do is we're trying to convince a verifier that we know a solution to the problem. Now, specifically how that works in this Kachina protocol is that the prover, this is off-chain computation. So off-chain, we have access to the private state. We're keeping the private state off-chain. We can perform a state transition between pairs of private and public states. And we can prove that the transition on the public state from u sub I to u sub I plus 1, given the initial private state, r sub I, is a valid transformation of the public state. And so if you go back to the slide where I introduced the idea of ZK SNARKs, it talks about a witness. The witness is the secret that we don't want to reveal. In this case, the private state is the witness. There's a statement that we're trying to prove, and the statement is public. The statement is that there exists a private state. We're not saying what it is. We're keeping that secret, such that the transition from the initial public state to the new public state is a valid transition. And we'll actually construct a proof of that, a ZK SNARK. So this is all performed off-chain in the Kachina model. And then what we'll do on-chain is we will only transition the public state, the initial public state, to the new public state. The transaction on chain includes the proof. So we'll send the proof to the chain. And now the proof, now the blockchain acts as a verifier. It verifies that this proof is a valid proof, which means that there exists somewhere a private state that will allow this transition to be valid according to the rules of the contract. It also has to check that the initial state of this transaction is the one that we expect. Because if it's not, we can't perform this transaction. So now I want to talk a little bit about how to make this practical. So this has been very abstract. There's a real problem with what I just talked about, which is I said that we have a proof that this transition on the public state is valid. We'll ask the blockchain to perform that transition. And in order for the blockchain to perform that transition, it only has to verify the proof and then verify that the initial public state is U sub I. But what happens if the blockchain finds itself in a different situation, a slightly different situation? It verifies that the proof checks out. The proof says you can go from state U sub I to U I plus 1. And then it checks to see if the state is U sub I, and it turns out that it's not. It's some other state U sub J. So why would this happen? Well, this is a decentralized blockchain, and it has running the smart contract. There are concurrent accesses to the smart contract. So there can be so-called contention, where when we ran the contract off-chain, constructed our proof, we saw a state U sub I. When we tried to perform the transaction on-chain, we saw a different state U sub J. So this, in general, we cannot allow this transition. And this will happen whenever somebody changes the state of the contract in this model. So we need to be a little bit more subtle. So what we'll do, so first of all, I said that this transaction should fail, and it should. We want this transaction to fail, and you can think of an easy scenario to convince yourself. Let's say that off-chain, I verify that I am in a public authorized set for an action in a contract, so I'm allowed to perform the action. And then I do a state transition that represents me performing the action I'm allowed to do. And I send that to the transaction to the chain. Meanwhile, on-chain, my authorization was revoked. Some administrator took that authorization away. I no longer have the right to perform that transition. Well, we would like the blockchain to reject that transaction because I'm no longer an authorized user. Whoever gets to the chain first with a state update should win, and the person who removed my authorization, they win. I can't do my transaction. That transaction should fail. There's a related transaction which should succeed, though. Let's say I verify that I'm authorized to perform an action, and I compute a state update of performing my action, prove that I'm authorized, everything's okay. Meanwhile, your authorization has been revoked. Well, that transaction should not fail just because the authorized set is different than it was before, because I'm still authorized. So we need to be a little more subtle about what parts of the public state, and it turns out private state, the transaction depends on. And so this is the last piece of the Kachina model that's important, so-called transcripts. So off-chain, we have a transition from a public state to a private state, or a pair of a public state and a private state to a new pair of a public state and a private state. And when we perform that transaction in Kachina, we will also compute so-called public and private transcripts. The private transcript is important, but I'm going to gloss over that because it's less important for what I'm talking about right now. The public transcript is a representation of the parts of the public state that I depended on, that I actually needed to read. And it also contains a representation of the transformation that I made on the public state. So it's sort of a diff of the public state that I cared about. The prover is going to prove that a public statement about the public transcript and a secret private transcript witness. So why this is important is that we don't have to send the full expected state as part of the transaction. We'll send the proof and we'll send the public transcript. And so now I find myself in U sub J, different from what I saw off-chain. And I don't care that it's not exactly the same state that I saw off-chain. All I care is that the transcript that I have is compatible with the state that I do see. And so this is a much more relaxed check. It means that I can avoid a lot of contention. And so this is the final ingredient of the Kachina model that we need to actually make this work. We'll check the proof that this transition is allowed. We'll check that the state that we do have is compatible with the transcript that we have. And if that's true, then this transition is allowed. So now we get to a concrete realization of this in the Midnight Network. This is exactly how transactions work in the Midnight Network. So this is a real diagram from some of our documentation. And it's just showing what is the transaction flow of a call in the Midnight Network. There's two boxes. On the left is the user's device. This is off-chain. On the right is the node. So this is on chain. And we should understand almost every line of this now. So the first thing that we do on the user's device is we fetch the public state. A there on that very first line on the left is the address of the contract. So the Midnight Network uses an account model where contract addresses map to the public state. We can fetch the public state from the chain. We can fetch the private state from somewhere. This is off chain. So this is kept in a database on your local machine, for instance, or some other representation of private state. It's off chain. And then we'll run the code off chain, the exec circuit JS. We compile the code to JavaScript. So we'll run some JavaScript code. It gets I as the input to the transaction. It gets the public state and the private state. The input, interestingly, is also private. It produces output, and it produces the transcripts, the public and the private transcripts. They're produced as a byproduct or a side effect of running the code for the transaction off chain. Given the address of the contract, we can fetch the so-called proving key, which is part of the ZK-SNARK protocol. And we can fetch something called ZKIR, which is the zero knowledge intermediate representation. This is a Midnight specific representation for what a proof contains, what a proof should contain. Both of these are produced by the compiler for our contract. So these are compiler produced artifacts. We'll just fetch them. We'll construct a proof off chain. So there's a proof server. Some users are running a proof server locally on their machine. Sometimes there's a proof server running in the cloud. This is a part of your trusted computing base. And you can see this because it's given the public transcript and the private transcript. So the private transcript contains private data. So you need to trust the proof server. You might be part of an organization like a bank or a hospital or something running some blockchain apps, and you might have an organization-wide proof server that is part of your trusted computing base, or you might just be running it locally on your machine because then you can trust that. The inputs to the proof are the public and private transcripts, the inputs to the transaction, the outputs from the transaction, the proving key, and the ZKIR representation of what the circuit encodes. This is the arithmetic circuit that I talked about, the problem of finding a arithmetic circuit solution. We'll construct a proof. The transaction contains the public transcript and the proof and the contract address, and we'll submit that transaction to the chain. So now you can see on the right what happens on chain. We get a transaction that contains a public transcript and a proof. Given the address of the contract, we can fetch the verifying key. This was also produced by the compiler. When the contract was deployed, this was uploaded to the chain. So the chain knows for that address, what's the verifying key. And then we'll verify. This is the verification part of the ZK-SNARK protocol. The verifier is going to use the proof and the public transcript and the verifying key to verify that the proof is correct. If the proof is correct, it'll get this public state. It'll try to apply the transcript to the public state. So this will be I said the transcript was contained a kind of diff of the public state that'll give a new state. If that succeeds, so it doesn't fail, then we can include this transaction in the block. This is what the node will do. So I want to talk a little bit about how we can make this even more practical, how we specifically do this in the Midnight Network. The first thing I want to talk about is a virtual machine that runs on chain called the Impact VM. I'm a programming language implementer and designer, and so I see everything as a programming problem, and you can always solve it by inventing a language, and Impact is a little programming language that runs on chain. This is a page from our documentation. It says the on-chain parts of programs that are written in Impact are on-chain VM language. You don't need to worry about it, but I'm telling you about it now. And then the second paragraph there says Impact is a stack-based, non-Turing complete state manipulation language. So what does that mean? Well, Impact is a very simple language. All it encodes is transformations on the public state of the contract. So it's a little program that runs. The only thing it does is reads a public state as input and produces a public state as output. Nothing more interesting than that. And non-Turing complete is a fancy computer sciencey way of saying that it can't do arbitrary, unrestricted computation. It's restricted. It's restricted to only doing public state rewrites. That's the only thing it has to do. That's all it can do. This is in contrast to the Ethereum virtual machine, for instance, that runs on the Ethereum blockchain, which is in a sense, Turing complete. So that the Ethereum virtual machine can really compute anything that you can compute with a computer. Um, this is not that virtual machine. So when you hear about the Impact VM and you think about a VM running on chain, you have to understand that in the Midnight Network, this is a really restricted VM that just does the public state updates for your contract. And then the question is, how do we represent the transcript, the public transcript? It's actually represented as an impact program. So the impact program encodes the public transcript part of this transaction processing. And I'll show you a little bit about what it looks like. This is a snippet from our implementation. All of the public state update operations are implemented using impact bytecode. This is a little machine language for this little machine. This is the operation to read or to look up a key in a map. We have maps in the ledger state. We can look up a key. We have a little domain-specific language that we use to write these. This is the code. There's 4 instructions here. Dupe, 2 IDXs, and a pop eq. And this, we said it was a stack machine. It runs with a stack. The program always starts with 3 values on the stack. There's at the bottom of the stack, the base of the stack is the context. On top of that is the effects, and on top of that is the current state of the current public state of the contract. And then if we look at this dupe instruction, it says dupe the value at index 0 in the stack, where the index counts down from the top of the stack. So 0 is the very top of the stack, and it just duplicates that. So now we have 2 copies of the state on top of the stack. And why you might do this is that operations will consume values from the stack. And so we might want to consume the state and still have it around. The next instruction is an indexing instruction, and that is going to extract a subpart of the state. You can ignore cached and you can ignore push path because they're not really important right here, but the path part of this is important, and the path is F. So F is an input to this operation in our little domain-specific language, and it is the actual path to the map in the ledger. The path might be the map might be at the top level of the ledger, sort of at the outermost level, and it might be really deep, nested inside of other data structures. We will have computed that path, and we'll just pass it to the program. And so this instruction is maybe a more complicated instruction. If you think about a cost model where we have to charge gas fees for running this instruction, I might have to do more work depending on how long the path is, because that tells how deep it has to look in the ledger. But it will still run as one instruction that fetches a subpart of the state, which is the map that we're interested in. The next instruction will index into that map, and it will fetch the value at a given key. And the way that this is implemented depends on the kind of thing it's indexing into, but it's indexing into a map. It'll fetch the value at a given key. So what we have now on top of the state on top of the stack is the value, and then the pop instruction will remove that, return it as the result of this operation. So here we have a little 4 instruction program that just looks up a value in the ledger. And this will become part of a transcript that reads from this map in the ledger. And as part of this transcript, the pop eq instruction, it means pop equal, will actually record the value that was read. So if this is reading my authorization, the key is my ID, and the authorization is whether I'm authorized to do that operation or not, that will be recorded in the public transcript as part of this operation. Here's another operation. This is inserting into a map. This one is a little more complicated, kind of the opposite of looking up a key, inserting a key and a value pair into a map. 5 instructions. I won't go through those step by step, but this updates the ledger state to include the updated map. The next thing I want to talk about that we've adopted as a way of making this practical is that we represent the arithmetic circuit that we need to prove using a little language called ZKIR. That's the Zero Knowledge Intermediate Representation, which we invented just exactly for this purpose. It has a JSON representation, so I'm showing a snippet of a JSON object. JSON is the JavaScript object notation. It just represents an object as if it were a JavaScript object literal. The ZKIR instructions are very low level because the arithmetic circuit that we're trying to build is a very, very low level representation of a restricted computation. It's basically a polynomial circuit with variables and constants. So The instructions here are low-level instructions. I don't expect you to understand this. What I would like you to appreciate is that this is not very easy to write by hand. So I'm talking about making this practical, but it's not really super practical yet. One interesting bit of this is here. This is private data. So I have a private transcript when I construct the proof. If you remember, the proof had as input a private transcript. This is fetching private data from the private transcript. And it's constraining it to have a certain structure. This little bit down here, this is part of the public transcript. This is actually the bytecode encoding of an impact program. So we talked about the impact program. The proof, in a sense, is about the on-chain public transcript that we ran, because the proof is that there exists a private state that makes this public state transition valid. And so the proof is about that public state transition, and that's actually encoded here with these public input and declare pub input. And PI is public input skip. These instructions are actually encoding of an impact program. So I want to transition now to talking about how we make this accessible. So writing impact code is not very accessible, and writing ZKIR code is not very accessible at all. The ZKIR program gets translated to a representation of the arithmetic circuit problem using a library called Midnight Circuits. And writing those, it's a Rust library. Writing API calls on that Rust library by hand is also pretty complicated. It's error prone. You have to keep track of things in your head. You have to get encodings right. It's really subtle. And there's no algorithmic content where you can look at the code and recognize a program. So the very first thing you do is you design a programming language that would allow you to compile a higher level programming language into these lower level representations, like bytecode that runs on chain and a representation of the zero knowledge proof. And so that's what we've done. We've built a programming language called Compact. The Compact programming language is based on the language TypeScript. We chose this because we expect that our decentralized app, or DApp, developers will be writing web apps in JavaScript or TypeScript, or perhaps mobile apps in React Native or something like that. And so we want a language which looks similar to TypeScript and feels a little bit like TypeScript. Um, the public state in Compact is declared as part of the ledger. So the abstraction of the public state in a Compact program is the ledger. The access to private state is through witness functions. So witnesses are functions that are implemented in a foreign language. The foreign language in this case is JavaScript or TypeScript. The Compact program can call them, but they're arbitrary computation that the Compact program doesn't know about. It calls out to them and gets back private values. And the Compact programming language, is intentionally limited by the requirement that we have to be able to compile it down to arithmetic circuits. So some of these limits, for instance, are there is not currently any recursion in Compact. There's not any unbounded iteration. In other words, there's no loop over an unknown number of iterations. It's always a fixed, known at compile time, bounded number of iterations. The data structures in Compact, things like arrays and other data structures, are always bounded fixed sizes. And this is because we have this requirement that we have to encode these into the zero knowledge circuit. We occasionally get feature requests, which are things like, could you add arbitrary length arrays? No, that's something that we don't know of a good way to do it. We don't know a good way to do it that would be performant, and that would result in circuits that were reasonably sized so that you could actually prove them in a reasonable amount of time or at all. Here's an example of Compact code. So this looks a little bit like TypeScript if you're used to reading TypeScript. If you're not used to reading TypeScript, you can read it like a pseudocode. This is one of our example applications, and it is an online election protocol. The protocol has voters are registered. There's a topic that they want to vote on. They first commit to their vote. There's a commitment phase. After everyone's committed to their vote, or enough voters have committed to their vote, they reveal their votes that they've pre-committed to. They can't change the vote that they've committed to, and then we can count the results of the election, and we can see who won, or whether the topic was voted up or down. It's a yes or no vote. This is a circuit that is called add voter, and it has some interaction of public and private state. We split the state into public and private bits. We can take a look at the public state of the voting contract. All of these ledger declarations, starting on line 24 and going down to line 32, are just parts of the public ledger state. So there is authority. That's the person who can administer the contract, and it's 32 bytes. So it's a hash of their secret identity somehow. The state of the contract is an enumeration or an enum, and it can go in a setup. It goes to a setup phase, and then where you're registering voters, setting up the topic, and then you commit to votes, and then you reveal votes, and then it goes to a final state when the election's over. The topic is just a string. Opaque means that this is JavaScript foreign data that is stored in the ledger, but Compact doesn't actually have access to it. We have some counters, we have some Merkle trees, we have some sets. This is all things that are stored in the public state of the contract. So this is all things that you can see. It's just in the blockchain. Here's the circuit again, and I circled the parts that are related to reading and writing to the public state. There's two reads and there's a write inserting into a Merkle tree, I think. So that these bits form the public transcript. But the programmer didn't have to think about public transcripts when they wrote the code. They just thought algorithmically of writing code in a TypeScript-like language. The public transcript will be automatically built when we run this code. This is the private data of the contract. These are witnesses. They're implemented as JavaScript functions you can call. They get some private stuff. The two bottom ones are workarounds around features that Compact doesn't yet have, so you can kind of ignore those. Those are a little bit ugly. I circled the private bits. So the input to the transaction is actually private. And then the calls to the two witnesses are private. So this will form the private transcript. And the programmer, again, is not thinking about the private transcript and building a private transcript. They're not thinking about public inputs and private inputs and public outputs from circuits. They're not thinking about the circuit at all in general. This is the same circuit I showed the ZKIR for before, and it's obviously a lot easier to read this and know what it's doing. So I just want to circle back to the full title of the talk, Making Zero-Knowledge Smart Contract Development Accessible, Secure, and Practical. So we started with just a programming model, a very abstract programming model, the Kachina model. We have a concrete realization of Kachina where we've had to make decisions about how we represent proofs, how we represent, or the content of proofs, how we represent on-chain public transcripts, how we provide access to private data. We've made a lot of choices there. And so the specifics of what we've done in the Midnight Network is that the contracts are written in Compact. The public ledger state is actually stored in the blockchain, in the Midnight blockchain. The transcripts are represented in this bytecode language that is this Midnight specific language we've designed just for public state updates. The compiler generates JavaScript code. And so the implementation of the contract when we're running off chain, constructing the private transcript, constructing the public transcript, this code is JavaScript. There's a runtime, which is sort of shared features that all contracts need. And this is implemented in TypeScript and WebAssembly. Some of the WebAssembly bits were written in Rust and compiled to WebAssembly. Their witness functions are foreign functions that have access to private data, and those are implemented in TypeScript or JavaScript. The representation of the arithmetic circuits is this ZKIR representation. And the actual transaction construction submission, this happens at I say higher in scare quotes, at a higher level of the stack. It might be lower depending on how you look at the stack. But there's a different level of the stack. It's outside the language that the language is not concerned with transactions or how they get constructed or how they actually go to the blockchain. That's a different level. So the language is agnostic to that. And then I just want to take a step back and talk more generally. What the Minakawa project is about is none of what we've designed or built here is particularly Midnight specific. So we've designed the whole architecture of the system to be flexible, that all of these things could be changed. So just in general, what potentially falls under the umbrella of this project that we have is other source languages are possible. You could come up with a different source language if you didn't like ours, or if you just had a different programming model at the source level, language model level, you could come up with a different source language. It could be like Python, or it could be like Haskell, or it could be whatever you wanted. Public state doesn't have to be in the blockchain. It can be anywhere. We've in the Midnight Network, it's in the blockchain, but you could have any repository of public state. It doesn't really matter. And the public transcripts could have almost any representation. We've abstracted out the representation of impact bytecode into the implementation of ledger operations that could be swapped out with some other implementation. The target language does not have to be JavaScript. You could generate Rust code, you could generate machine code, you could generate anything you wanted. The runtime is, we have a runtime implementation in TypeScript and WASM, but you could have any other runtime implementation. The witness functions could be in any other language. The arithmetic circuits could have other representations. You could represent them directly as API calls on some zero knowledge library. You could represent them as some other representation. So none of that is assumed by the architecture that we've built for the Minokawa project. And that is the quick tour of how zero knowledge proofs can be practical and accessible and secure. I see a comment. I see a question from Gabriel in the chat, and so Gabriel's question is how to generate, for example, Rust code with the compact compiler. Is that already available in the release compact C? So no. So the question is, how could you generate, for instance, Rust code if you wanted? It's not available. That would take some work. We've built the compiler so that it has a number of, compilers are normally structured as a number of passes, where they take an input, each pass takes an input language, produces an output language, and they transform the input language to the output language. We've written the compiler pipeline to have very many passes, maybe on the order of 30 passes. They all do a small amount of work. We call this a nanopass architecture. And what you would do if you wanted to generate Rust code instead of TypeScript is, it's only the very back end of the compiler. It's only the very, there's two passes that have any knowledge of TypeScript whatsoever. So one is called prepare for TypeScript and one is called print TypeScript. And you would just replace those with a Rust code generator. So it's a small amount. We expect that it would be a small amount of the compiler that you would have to replace to generate Rust code, for instance. The TypeScript code depends on the TypeScript, the runtime library. And so you'd have to provide a Rust implementation of that, or an implementation that was accessible to Rust in some way. So that would be a larger implementation task. We haven't done it, so we don't actually know how much effort it is. We hope it's a small amount of effort. We've architected it that way, but we don't know for sure. Are there other questions?
If there aren't other questions for now, I will say people are welcome to digest this information and then follow up. This is an open community. There'll always be another opportunity to join another call or join another event or join us on Discord. So please do, follow up if you want to get more involved in Minakawa. And I'll send a link around to everyone who signed up with the links to this recording and the slides so you can take a closer look at everything, and also a link to the calendar so you can join upcoming calls. Oh, and I see one more question just came in.
Yeah, let me dig up the link. I can drop it in the chat. I just need to dig it up in a second. It was it's in the Midnight Docs. It got buried several levels deep, so it's a little hard to find nowadays. So this is a link to the Impact VM documentation that I included a screenshot for. It's sort of Spartan as documentation goes. So it would be nice to have contributions to improve this documentation, for instance. So questions are coming in. What security concerns do we have? So I'm not a security researcher. And I think that I can't even really speculate on what security concerns I have. I do have a concern, is that the programming model is complicated. And if decentralized application developers don't understand the security model, then they'll make mistakes. So one thing that I've noticed a lot is that the witnesses, the private data, are not something you can trust. And people will write dApps that trust that the witnesses tell the truth, for instance. So one example that we sometimes use, it's kind of trivial, but we use an example of age verification, where you want to keep your birthday private, but you want to verify that you're older than a certain age. And so you write a witness that returns your age, but you can't trust that witness. I can just lie about my age. So if I'm 13 years old and you need me to be 21, I'll just tell you I'm 20, 24. So that's not secure from that standpoint. You would actually need to have that age would have to be signed by an authority that you trusted, so that you could actually trust it. And so I think that's one thing that I'm concerned about, is that people don't understand the security model when they're writing applications, and we need to make that possible for them. Um, do we have other code examples of the impact language? In the repository, so the repository is not actually open sourced yet. I expect it very soon, like in the matter of a week or two. And there are examples of um, other library routines, other ledger data types that are implemented in impact code. Now, right now, impact is not something that you as a user can really write. You could provide new operations by writing them in the compiler, rebuilding the compiler, and then you would have the new operations available. But we haven't built the system yet that you could write impact code yourself. That would be a potential future feature, is that you could implement your own public state types by just writing impact code directly in your contracts. Um, Midnight in testnet and or mainnet testnet right now. Um, so it's going to mainnet, marching towards mainnet. Um, um, how does the impact language integrate into a REST program? So the way that the impact language works in TypeScript is we actually have a Rust implementation of the impact VM that is compiled to WASM, and the TypeScript code calls impact instruct. We use impact offline when you run the dApp. The TypeScript code calls the impact VM with a representation of the program, and it gets back the public transcript and the results of running that program. Um, so I think integrating impact into a Rust runtime would be actually easier. We're jumping through some hoops to get it to work from TypeScript, and I think it'd be just more direct in Rust. So the implementation in your offline dApp is exactly the same Rust code that's running in the ledger, compiled to WASM. There's another question, a related question from Daniel. What challenges do we encounter running the Impact VM? I don't think there's a lot of challenges there. It's super simple. It doesn't do anything very complicated. We've thought about future language features that might require changes to the Impact VM, and those could potentially be challenging to support. But right now, the language is very, very simple. And I think that we didn't use any Rust libraries, other than it's really just an implementation by hand. The number of instructions is very small. The implementation of the instructions is pretty simple. Do we have any corporate backers or partners? We have a lot of partnerships. So one of the things that we want as part of the Midnight project is that when the blockchain goes to mainnet, we have a lot of useful and decentralized applications, dApps, and that we have a lot of great examples of the kinds of things that really show off the chain. So we are working with a lot of partners who are doing things in sort of DeFi spaces, DEXs, games, different token standards. So there's a lot of that's going on around partnerships as well. Yeah. And I don't really know much about. I can't say much about those because I don't actually know much about those. The DApp that has been written with Midnight/Impact. We have some example DApps. There's one example DApp that we have built that I don't know if we've open sourced. It's a little DAO, and we have this election. We have this election DApp. We have some sort of kind of really simple DEX like DApps that do swaps. Um, the so one thing that you need to keep in mind is you're not actually going to write impact code. So the ledger operations are implemented in impact, but it really is an implementation. It's a implementation decision that we used, or implementation detail, for instance, that we used impact. We could change that. We're not actually promising right now that impact is a stable ABI that you could use yourself on the Midnight chain. We might change it with every and break existing impact code. So your way to get interaction with the chain is to write compact code right now. Daniel has another question. What are the advantages of building a DAO with your system versus another blockchain? This is an interesting question. I actually can't speak um, very authoritatively to questions like that. I am a programming language designer and implementer, and so like blockchain and Web3 stuff is a little bit outside of my area of expertise, honestly. Um, One thing that is interesting, or that I think is worth noting, is that for any specific thing that you want to build, there is some solution that you can come up with in a traditional smart contract system like Ethereum, potentially with some off-chain support somehow. And so what we're really providing is a model where you can realize um, a lot of the things that you want to do without having to come up with those sort of custom ad hoc bespoke solutions, where you can realize a lot in a very flexible way, in a very flexible programming model. And then David mentions in the chat, if you haven't seen it, that there is another meetup happening in this same Zoom room in about 5 minutes, and you're welcome to stay for that. It looks interesting. All right, I think I'll wrap up here. As David said, the code is not yet available for you to look at. It will be hopefully in the next week or two. And then I would love to start having like interaction. We'll have a GitHub repository, and we can start getting interaction there. One of the things that we're really committed to is doing a like language design in the open, for instance. So we'll have a process where we can get feature requests, and we can get proposals, and we can then evaluate those proposals, decide that a feature is ready for implementation, that it's well designed and well specified, and that it meets the standard that we have. And then there's some transparency about what the roadmap is and what's coming in the language.
Great. Well, thank you, Kevin. Appreciate you sharing all that information. And again, I'll send everybody who signed up all these links and resources. And then we look forward to seeing you in the community going forward. And I'm going to stop the live stream for this event. So, Kevin, I'll send you the link to where the recording will be. And then for